So we're very happy and privileged to have the father of TensorFlow answering some questions. We have some sample questions which I can read, but feel free to also ask more if we have time. So the first question, and some of them were people were submitted. There was a form that says, how much do I need to worry about task and data parallelization with TensorFlow when I work on a single machine with or without a GPU?
Sure. Thanks, Nick. So as I mentioned this morning, especially for the simple cases like this, single machine, you should not have to worry about this at all. In most cases, TensorFlow will take care of it completely for you. There are some very specialized cases where you might want to optimize, but in most cases you want to start with not doing anything, just take the basics, go from there, and then maybe fine-tune if you really need to.
Okay, so the next question is, what's the best way to load my data? Feed dictionary or use a queue?
Yeah, so this one's interesting where if you have small amounts of data, let's say it fits all in memory, then feed dict is a great way because you can just load everything in memory, use your regular Python to loop through the data and feed that in as you're training the process. But if you have lots of data, say on a distributed file system or even a local file system, and you want to do, you don't want to be limited by the I/O, then queues are a great way for you to, overlap the I/O that's going on and maybe even have multiple threads doing the I/O if you're, say, going against a distributed file system while you have the actual processing going on in a different thread.
Okay, so the next one is, are there any optimization that the compiler or the interpreter does on the declared execution graph that I should be aware of? Are there expressions that they kind of got like optimized together or?
Right. There's actually a lot happening there. Some of the more common ones are things like constant folding and constant propagation, where let's say you have constants in there that are always going to remain constant. We don't want to continue to do the same operations again and again. So the first time we run it, we'll try to elite them and do all of that computation up front. There are more advanced things that we're working on as well, where let's say you have operations that always go together, or say two component-wise things one after the other. So we're working on things that will automatically fuse them together without having to go through the memory again and again. So basically give you speed-ups without having to think about that.
Okay, so this is coming from somebody who said, well, I tried to multiply two matrices with TensorFlow, and then I tried with SciPy, and SciPy seemed to be twice as fast. And the question is, when does TensorFlow become faster than SciPy? In which cases would I prefer to run SciPy versus TensorFlow? Or what's the reason why? What's the overhead over there that makes it a bit slower?
Right. So I would say if your computation is very, very small, if your matrices are 5 by 5 or really small sizes, you'll probably not see much gains from TensorFlow. It's likely going to be slower than anything basic you do, maybe your own multiplies as well. But as you grow that, or as you're doing more complex expressions, and when you're trying to iterate over that many, many, many times, so for example, you create a graph and you typically train that model across thousands of iterations, then any overhead it has early on for the pre-compilation, etc., that will go away and you'll start to see more gains. And these are areas that, again, every iteration that we do every month, every day we really put out new things, so you'll see improvements over time as well.
So the next question is there any performance difference running TensorFlow in C++ versus Python? Some people have said that whenever you start a session, you're incurring some extra system calls. Is that something that you're avoiding? Is there any case where C++ execution of TensorFlow would be faster or more preferable than Python?
So we use both very commonly. So our most common cases, we use Python for our training efforts. So if you're training a model, use Python because it gives you a lot of flexibility in what you want to do the loops, etc. Whereas for production deployments where you care about that last millisecond of performance, we do use C++. Partly because Python itself has overheads. If you, for example, want to run multi-threaded code there's the locking isn't great. There are lots of issues with Python in those areas. So we typically recommend for production deployments using C++ or maybe Java and other languages that are that we've been adding lately, support for lately.
So how is it once I've made it in Python to translate it to C++? It's kind of like a one-on-one?
So you literally don't have to do much. There's already an API to save the model. It's basically saved, and that same model can be loaded in C++ directly. So you don't have to do much. The underlying code is in C++ in both cases. So it literally runs the same way, whether from Python or C++. Just the APIs are different.
So, I know that you've implemented a lot of algorithms in TF-learn, contrib-learn. And are there any components or are there any tutorials about how you can reuse these components so that, and are there any gain benefits and any benefits you can gain by reusing these components to, code your latest NIPS deep learning algorithm, like the estimator class, for example? Does it offer anything in terms of performance?
Usually no. What we are trying to, I would say, performance-wise, we've things that are clearly separate components, we've tried to make them as components, and there's this notion of a supervisor that you can use with or without estimators, and estimators also use those internally. And the idea there is much more about getting the best APIs, getting the right design patterns for you to emulate and copy, less so about performance that you should be able to get in both cases. Over time you'll see just more and more examples that we have, make sure all the right things are there in the right way.
Okay, so we're question number 7. I know that there's a whole chapter about how to write your own operations, own nodes in TensorFlow, especially in C++. And I've seen that you've actually implemented a lot of utility functions like cross-entropy. Now the question is, if I implement cross-entropy with TF operators like multiplication and additions versus using the one that you've implemented low level, is there a big difference? Is there more overhead if I implement it on my own?
So today there would be some, and that's basically why we implemented the C++ one. The reason is there are overheads in combining these, running 10 operators versus a single operator today. What we're working on is a compiler-style backend that automatically takes your graph at runtime, basically does a just-in-time compilation the first time you run it, and replaces it with customized code, and that should get rid of most of this overhead. So in the future, you'll see much less of a need to do this.
We'll leave for the future. Okay, so the next one is a bit provocative. How does TensorFlow compare to MXNet?
There are many different frameworks out there. We decided to write TensorFlow because we saw that the other frameworks weren't meeting the needs of what we needed. Most of these, including MXNet, have come out of academia, even though in some cases, there are other groups trying to make them better. We are really, putting in a lot of effort on TensorFlow, and a lot of folks like yourselves as well in building this community. And I see the strength of TensorFlow being the community and the rate at which we continue to improve it. It is a good platform today to use, but it's going to continue to get better over time as well.
So the next question is coming up a lot, which is, are there any algorithms where TensorFlow is inefficient or it would never be able to run well? Like, for example, what if I want to run graph algorithms, or what if I want to run code decision tree, a random forest? It always comes when you go to a manager, they ask you, does this thing run boosted trees?
Actually, it does run random forest, but I don't know if the implementation is reasonable. I wouldn't say it's world class, I guess, or the best. There's the place we started with TensorFlow was deep learning, so it's definitely very, very optimized for that. There are many other algorithms implemented there now: linear regression, logistic regression, random forest, SVMs, and we'll see more over time. It does not do graph algorithms today, but at its core, the way we've layered it is it's a pretty general purpose computation engine that you can use for a lot of things. Of course, to get the most performance out of any specific thing, it's always possible to write a very custom library, hard-coded, hand-coded in C++ that maybe is better. But the strength here is that mix of performance and flexibility that you can really put things
So you
together.
do have an implementation of decision trees, because I haven't seen it. Is it like internal or?
No, it's external.
It's
actually.
external. Okay,
It's external,
we'll
yeah.
take a look at that.
Yeah.
Now we know that TensorFlow distributed a multi-GPU. Does it do both of them at the same time? Do we have to do any extra plumbing for that?
It does do both together. There are some examples, I believe. You could use just many GPU machines with a single GPU itself, or split across multiple GPUs per machine, where maybe you do something different locally on a machine. Say you're just adding up the gradients, whereas across machines you can do asynchronous stuff as well, or synchronous, and it really supports both.
So the last question, and depending on your stamina, we can have more questions from the audience, is if we use the estimator class or everything that it's implemented, like the multi-layer perceptron or the linear classifiers, do we have to worry about distribution and GPU? Can we just take the linear classifier and say run in 1,000 machines, or do we have to do anything extra?
It's getting there. I think some of that integration is a work in progress, but that's the direction we're headed towards.
Okay. So, do you think we have more time? I mean, we have time. Are you doing?
Sure.
Okay. So, we're gonna do the questions for another. We have to start at 2. So, raise your hand, and I'll come with a microphone. Okay. Coming.
How large is the core development team in Google for TensorFlow?
So I think this morning I was mentioning we have almost 500 contributors now. I believe, and it's sort of rough, it's hard for us to say exactly, but maybe 100 or so of those are at Google.
So I wanted to ask if at all I want to do a data parallelization on TensorFlow, how would you do it? So, symbolically, if I just give one large input and I want to just give a command, okay, split it into 4 GPUs, how should I do it?
So there are examples actually on the web that you can probably start from, I would say. That's the best. If you have the 4 GPUs on a single machine, then you can actually farm off work to each of the GPUs from just one input. And like I was mentioning, you can have a queue, and you have 4 independent threads reading from that same queue that process on the different GPUs. So that, there are some really nice examples, I think, for something like this that you could try to start with.
Can you talk a little bit about TensorFlow plus Cloud ML and some of the work that's being done there on hyperparameter tuning? Is it running on TPUs? Is it auto-scaling? All that stuff.
Sure. So the idea there in Google Cloud ML is to really make it easy and fully managed to run TensorFlow. So all the stuff that you're doing maybe on your machine or a single GPU or a single machine, you can easily scale across multiple machines, get the elasticity of the cloud, maybe run across as many GPUs or machines that you need. And there is a hyperparameter tuning service there that you can use to spread the load across multiple models, etc., or train different kinds of parameters. In terms of auto-scaling, once you have a trained model, you can actually auto-scale across. You can do predictions there as well. So you basically get a simple API that you can make as many calls, and it'll auto-scale that for you. So lots of stuff going on there.
What was most challenging factor that you faced when you were developing TensorFlow at Google?
So, this is a version 2 of our experience doing something like this. So the first one took a while to build. We experimented with it for like 2-3 years and used it quite a bit. As we were doing this, one interesting aspect was just going from version 1 to version 2. We built this from scratch, so there were differences, but then finding all those issues that are slightly different, matching things up, etc., took us a long time to get right, and we've learned a lot through that process. We also realized how simple things sometimes make a big difference, and we've tried to make it easier in TensorFlow over time to not make those mistakes too.
Is there any plan in your future to implement any API like, say, deep reinforcement learning? The reason for asking this question is these are the things which require, very, very process heavy, process intensive for calculating the rewards, and there is a scope for highly parallelizing the data path. So if you can throw some light on that.
Yeah, there's definitely interest in making more reinforcement learning things available. We aren't working on a specific API yet, but we are looking at starting with a few examples in how best to do that. We've been using it for our research today. We haven't spent as much time in making it a more general framework and looking at that.
How did you decide what to implement on the TPU ASIC, and what kind of benefit do you see from it?
So there isn't a lot I can say about that, except there is, at Google we care a lot about this problem of being able to run the large computation that's required for these models, and we realized that being able to do something more custom, we can take advantage of that and do much better than what's out there. And so that was really our goal. And in that area, that's how we started looking at what kinds of things do we want to do, then work it down and basically design that from there.
Hi, I understand that one of the future versions of C++ is going to include heterogeneous computing. Is Google involved in, working on that at all? Thanks.
Sorry, I have no idea if Google is involved or not. Yeah.
Alex, any questions for TensorFlow? No? Okay, let's do 3 more questions, and then we have to start the next session. So, I don't see any hands. 1. And then question 2. If we don't have more, okay. Don't be shy, because we don't have time.
What do you see as the future for TensorFlow in the next 5 to 10 years? Where do you expand?
Yeah, 5 to 10 years is a long time for this field. We've, did not exist 5 years ago. In fact, the prior version also barely was just started. I think as this field changes, we'll definitely see a lot of changes, both in terms of hardware, the kind of platforms that we push, and also in the algorithms. And, being able to leverage more and more compute will continue to be an issue, continue to be important. So I would still say performance, flexibility, and probably the portability as well. All of those will continue to be big.
Okay. Well, I can tell you, if TensorFlow continues like that, in 5 years he will be retired. So, so one last question. Okay, here you go. Lucky you.
Do you plan to implement TensorFlow over the Xeon Phi?
I'm sorry, could you?
Do you plan to implement TensorFlow over the Intel Xeon Phi?
Xeon Phi. Yes. So it already runs on the CPU processors, and we are looking at how we can optimize it for all kinds of chips. And totally, that's definitely something we want to make sure it works well on.
Yeah. Okay. Rajat, thank you very much again. Thanks for coming and doing double duty. Let's all wish good luck and even more success with TensorFlow in the future. So.